Welcome to the deep dive. We're here to cut through that constant information overload and really bring you the nuggets of knowledge that matter. In a world just awash with data, especially visual data, how do you quickly get to the core of what's important? Sometimes an image, well, it isn't just there to be seen. You need to engage with it, almost interrogate it. So today we're taking a deep dive into time. It's a fascinating new approach in multimodal large language models, MLLMs, and this isn't just about AI looking at pictures anymore. It's about teaching AI to, well, think beyond images. Our mission here is to unpack this really innovative step in AI reasoning. We want to understand how it's fundamentally changing the way these models interact with the visual world around us.
Yeah, that's really the core of what we're digging into here. Our main source is this research paper. It's titled Thyme, Think Beyond Images. Came out August 2025. It's from a collaborative team led by Yifan Zhang. And the paper introduces this model, Thyme, that it moves MLLMs past their current limits. It empowers them to autonomously generate and then execute code. And this is for some pretty sophisticated image processing and even complex computations.
Okay, so picture this. An AI that could not just see an image, but could dynamically manipulate it. Cropping, rotating, enhancing it, maybe even performing calculations right on the visual data itself, all just to better understand what you're asking it. That's the kind of powerful capability Thyme is bringing forward. Now, MLLMs, they've certainly made progress recently, right? They started to think with images, incorporating visual stuff into their reasoning. But there were some real roadblocks with the older ways.
Well, absolutely. The paper points out two main categories of these existing methods and their limitations. First, you had generated images. This is where models would create sort of auxiliary images to help them reason. Think like sketching lines on a problem to solve it. It's a clever idea. But these generated images, they often lack the fine detail you need for real precision. Plus, they were computationally expensive, made real-time use pretty difficult. Then the second approach, it focused just on cropping. So models learned to identify and, crop the relevant bits of an image, basically putting a box around what matters. And that did help sharpen the AI's perception, reduce that hallucination issue where the AI just makes things up. But its functionality was really limited to just simple cropping. Didn't have the rich operations you might see in some advanced proprietary models, things like rotation, contrast boosting, running code. And this gap, this functionality gap in open source MLMs, that's really what Thyme is designed to address.
Right. So it sounds less like patching a hole and more like building something genuinely new. How
Mhm.
does Thyme actually achieve this kind of paradigm shift?
Thyme is really built on four core principles that set it apart. First is rich functionality. It supports a whole range of common image operations, not just cropping, but scaling, rotating, contrast enhancement too. And alongside that, the ability to do complex math. Second, and this is really key, is high autonomy. The model doesn't just wait for instructions on how to fiddle with the image. It intelligently decides whether to do something, what operation to use, and how to do it by generating and running code dynamically, all without needing a human to step in for each specific task. The third principle is efficient end-to-end training. They use this two-stage approach, supervised fine-tuning, SFT, plus reinforcement learning, RL. It's designed to keep training costs down while unlocking these advanced skills pretty quickly. That SFT stage alone, remarkably efficient, only about 200 GPU hours. And finally, the payoff for all this, significant and stable performance gains. Thyme consistently shows really substantial improvements across, I think it's nearly 20 different benchmarks. Covers everything from basic perception to complex reasoning general tasks. Figure 1 in the paper shows it quite clearly.
Okay, wow. So this isn't just a small step up. It really changes the game. The image goes from being a static background to an active participant, right? A dynamic tool the AI uses to figure things out. It's not just looking. It's actively probing and manipulating. So if that's the what, let's talk about the how. What's the ingenuity here? What's the kind of secret sauce behind Thyme's ability to learn all this? The training process must be pretty sophisticated.
It definitely is. Thyme uses that two-stage training strategy, and it's meticulously designed. Stage 1 is supervised fine-tuning, SFT. For this, they built a really high-quality data set, about 500,000 samples, carefully curated from over 4 million raw data points. And this dataset is incredibly diverse. It covers tasks needing no code at all, tasks needing image operations like cropping or rotation, even complex math problems that need code. It also includes these multi-turn interactive scenarios. You can think of it like the AI having a bit of a back and forth, like zooming in step by step or correcting its own mistakes. But the clever part of this SFT training is how it focuses the learning. For example, they mask the internal sandbox outputs during training. This stops what they call gradient contamination, Basically means the AI isn't getting sidetracked trying to learn how its own tools work. It stays focused on solving your actual problem.
Ah, okay. Makes sense.
Yeah, and also, in those multi-turn dialogues, it's trained to only focus on the final correct answer from the very last turn. This stops it from learning to, say, deliberately make mistakes early on just so it can look smart by correcting them later. And to make sure it's good at both images and math, they have this dedicated math data annealing phase. It's like a math boot camp. It gets fine-tuned just on math data using a lower learning rate, really helping it master generating that complex computation code.
Okay, that's stage one. What about stage two, the reinforcement learning?
Right, stage two, reinforcement learning, or RL. The data set here includes public data, sure, but critically, they added 10,000 manually collected and annotated high-resolution images, and these images are deliberately tough. They feature tiny, hard-to-see objects, things taking up maybe 5% or less of the whole image. This data set is specifically built to really push the model's perception skills for challenging stuff like reading tiny text, spotting specific attributes, understanding charts.
And the algorithm for this RL stage, you mentioned it was particularly clever.
Yes, this is where it gets really interesting. They use something called adaptive temperature sampling within their core RL algorithm. Think of it like,
Yeah.
well, like a person switching between brainstorming and detailed work. When Time generates text, like explaining its reasoning, it's allowed to be a bit more exploratory.
Right.
But when it writes code, it switches gears. It becomes incredibly precise, like a zero mistakes allowed mode.
Why the switch?
Because code is fragile. Even one wrong character can break the whole thing. So this adaptive approach stops it from generating invalid code. But it also prevents the model from getting too cautious and just avoiding code altogether, which would kind of defeat the whole point. And the model is incentivized using a mix of rewards. It gets rewarded for getting the right result, obviously, but also for making sure its reasoning is consistent with the answer and for using the correct formatting.
That's a really detailed look at the engineering. It certainly highlights the careful thought that went into building this capability. Let's shift to some real-world examples. The paper has case studies, right? How does Time actually perform when it's put to the test? It's one thing to talk principles, another to see it work.
Definitely. The case studies, especially figures 2 and then 8 through 13, they showed off quite well. Take cropping and zooming. Time might see a tiny distant street sign, maybe it reads Michigan Avenue, or a really faint phone number on a building far away. It then decides, all on its own, okay, I need to crop and zoom here. It generates the Python code for that, runs it safely, and then reads the newly enhanced image to give you the correct answer. There's even an example where it crops an image just to confirm that no, there were definitely no awning tricycles in that scene. Very specific.
So it uses cropping not just to read something, but also to confirm absence. Interesting. What about rotation or contrast?
Yep, rotation and contrast enhancement too. It shows time correcting, say, a slanted mathematical formula in a picture. It figures out the angle is wrong, generates code to rotate it correctly, and then it can transcribe it accurately, maybe into LaTeX format for scientific documents. Another great example is enhancing a really low contrast image. Maybe there's faint text you can barely see, like the word communities. Time enhances it using code, making it clear enough for reliable OCR optical character recognition.
And complex calculations, does it handle those within this framework?
It does. Under complex calculations, the paper gives an example of a multi-step math problem, something like figuring out cooking constants for a goose based on its mass and cooking time. Time first deduces the necessary mathematical expressions from the problem description, then generates Python code to actually compute those values, and finally provides the precise numerical answer, all integrated into its reasoning.
That autonomous problem solving is, well, it's quite elegant, isn't it? It's not just pattern recognition, it's actively adapting and manipulating the visual input to find the solution. So with all the sophisticated training and these impressive examples, what do the overall performance numbers look like for Time?
The evaluations are very strong. Time shows significant, consistent gains across almost 20 different multimodal benchmarks. It really shines on those tough, high-resolution perception tasks and complex reasoning problems. In fact, the paper notes it even outperforms some larger models, like Twin 2.5 VL32B, on certain perception benchmarks. Tables 3 and 4 show this. It suggests that just making models bigger isn't the only way to improve perception. Time's dynamic approach offers a really effective alternative.
But no model is perfect. Does the paper discuss any downsides or areas where it struggles?
Yes, they're quite transparent about what they call bad cases. For instance, sometimes Time might not use code, even when it seems like it would be really helpful for a complex problem. Or, conversely, it might sometimes use code for a really trivial calculation, where it's just unnecessary overhead. They also mention occasional inaccurate cropping, like it might crop the wrong area but still somehow stumble upon the right final answer, which isn't ideal reasoning.
And limitations of the approach itself.
The paper points out a couple of key things. First, Time's ultimate performance is still tied to the capabilities of the underlying base model. How good is it at precise object localization to begin with, or generating flawless code? A stronger base model could potentially boost Time's results even further. Second, there's a limitation in how we evaluate these things currently. Existing benchmarks don't always have robust ways to numerically score certain manipulations, like how well rotation was corrected or how much contrast enhancement actually helped. So it's a bit hard to fully quantify the success of those specific operations just using current standard tests, because those scenarios aren't well represented yet.
Okay, so we've journeyed through Time, its core ideas, the clever training, the practical examples, and the performance. What we've really seen today feels like more than just an incremental update. It seems like a fundamental shift in how AI interacts with the visual world. It's about turning those static images into dynamic, interactive tools for, well, for deeper understanding.
That's a great way to put it. Time really is a significant open source step. It empowers these MLMs not just to process images anymore, but to actively interrogate them, transform them as a core part of how they reason. It pushes the boundaries.
So let's leave you with this thought, building on what the research suggests. Imagine a future where every image isn't just something static you look at. Imagine it's something you can actively think with, where the visual information itself becomes this dynamic partner in solving problems. What kinds of new questions might we be able to ask then? What new insights might we uncover when our AI tools can genuinely think beyond images right alongside us?